In this video, we will be covering the topics from Math 277 Week 9, which talk about directional derivatives, implicit differentiation, and a couple other helpful tools that we can use, such as maximum and minimum rates, which we can use to apply to real-life scenarios. The first thing I'd like to talk about is directional derivatives. So if we have a vector here, we know from other courses that a unit vector is in the same direction as a vector with a magnitude of 1. So when we talk about directional derivatives, as illustrated in this slide, is the derivative of a function at point P directed in the direction of some unit vector. So let me just zoom in on this a little bit. So this is like saying the partial derivative of x with respect to some constant and the partial derivative of y multiplied by another constant, and the partial derivative with respect to z multiplied by another constant, where our a, b, and c values correspond to the coordinates of a unit vector. So we can kind of break these out. We can extract these a, b, and c terms to get our unit vector. So this is the direction that our vector is going to be directed along. And this is expressed as a dot product to each of our partial derivatives with respect to our function. And this we already had experience in our last video. This is just our gradient, right? So when we use this to solve for our normal vector, and we now can use it to solve for directional derivatives. So we can express this equation as our directional derivative, which is capital D, with our sub u. So that means we're taking the dot product of it, we're taking our gradient. So then this is expressed as our gradient with a dot product in our unit vector, which will direct our vector in that direction. So if we were to do an example of this, we want to find the directional derivative of this function here. So we know our directional derivative is equal to our gradient of f at a certain point P with our dot product of u. So this is like saying y, is that plus? Sorry, no, that's comma. We only have two variables here, so we only need to take two partial derivatives. So then with respect to y, and then dot product our unit vector, which is given to us as 12 over 13, then negative 5 over 13. So this one should be nice and easy. So let's get to it. This is equal to, so I'll do this one in red. So this is equal to 2x minus y in our first one. Then in orange, I'll do the second one, or in yellow, I'll do the second one. And this is equal to, this is negative x plus 20y. And this is with the dot product of our unit vector. So we're going to take both of the I components and multiply them together. So this is this one and this one. So this is 2x minus y, and it's multiplied by 12 over 13. And this is going to be minus x plus 20y, and then minus 15 over 13 from our unit vector. So I'm going to simplify this first, then plug in for our values. So this is going to be, so for our first term, this is going to be 24 over 13x minus 12 over 13y, and this is going to be negative x. Sorry, I'll put a plus here, put that in here. Okay, so this is going to be positive 5 over 13x, and this is going to be negative 20 times 5, 100 over 13y. Okay, so when we simplify this out, this is going to be 24 plus 5 over 13. So it's 29 over 13 in our x. And this is 12, so this is 112 over 13. Sorry, minus 112 over 13 for our y. And when we plug in for our x and y values, which are given in this initial point, which I'm going to highlight in purple, when we plug for those values, so this is 29 over 13, and our x is 6, then minus 112 over 13, and our y is negative 1, this becomes, so 29 times 6, 174 over 13, and this is plus 112 over 13. 174 plus 112 is 286 over 13. And is it divisible? Yes, it is. So then our final answer for our directional derivative is 22. So as you can see, this process will give you a scalar value. Okay, so for question 20, given this equation, we want to find the directional derivative in the direction from our point P towards Q. So in this case, we're not given a unit vector. So the first thing I would do is find the unit vector. Okay, so we are directing from P to Q. This is equal to our Q minus our P values for our X and our Y. So we're given, okay, hold on, I can write this out better. Okay, so for Q, we have, so it's going to be Q minus P. So this is 1, 0, and 1. And this is minus our point P, which I'm going to highlight in green, which is 1, 1, negative 1. So we have coordinates. We would do this one and that one. So this is negative 1, minus 1, negative 2. This is 0, minus 1. So this is negative 1. And this is 1 plus 1. So this is 2. Okay, and to find our unit vector for P and Q, this is equal to our vector, PQ, over the magnitude of that vector. It's equal to negative 2, negative 1, and 2. And this is all over, so this is 4 plus 1, which is equal to the square root of 9, which is equal to 3. So I'm flying through this because I've had lots of practice, but you can always slow it down. Okay, and this is negative 2 over 3, negative 1 over 3, and positive 2 over 3. So this is our unit vector. So I'm going to just highlight this in pink. Okay, and now we can find our directional derivative. So we have 3 variables now. So that means we're going to need the partial fractions of, so we'll use fx, x, y, z. Then we have partial derivative of y and partial derivative of our z. And this is to the dot product of our unit vector, which we just found, which is directed from P to Q. Okay, so when we do that, Just going to need to rewrite the equation in our lower half so I can work on this part. So this is our function is equal to x squared plus y squared plus z squared minus x, y, z. And our values that we're going to plug in are going to be from our starting point, which is p. So that's going to be our points. This x equals 1, y equals 1, z equals -1. Okay. So when we do this, so we're going to start with respect to x first. This is equal to 2x minus yz. With respect to y, this is 2y minus xz. And with respect to z, this is 2z minus xy. And this is multiplied by our unit vector, which we found to be -2 over 3, -1 over 3, and +2 over 3. Okay, so this is going to give us, this is 2x minus yz. This is -2 over 3 from our unit vector, plus our second y terms. So this is 2y minus xz, -1 over 3, and plus 2z minus xy, multiplied by 2 over 3. Okay, and I'm going to plug in for our values of our variables here. So this is 1. And this is going to be 1 times -1, so that's going to be +1. Okay, and then y is just 1, so we can get rid of that. And this is going to be +1. And it's going to be -2 minus 1. So -2 minus 1. Okay, so we can simplify this to be 3 plus Okay, so when we add this all together, this gives us -2 minus 1 minus 2 is equal to -5. All right, so now we're going to talk about maximum and minimum rates. So given what you already know about dot product, you know that the dot product of two vectors is equal to the magnitude of both of them multiplied by cos theta, where the theta represents the angle that is formed between the two vectors. So if we made this in terms of our unit vector and our gradient,